Look up the next time you walk under a concrete overpass, or the next time you step into a high-rise lobby with a concrete ceiling hanging 40 feet above your head, or the next time you drive across a concrete bridge carrying thousands of vehicles every single day. It feels permanent. It feels unbreakable. It looks like the most solid, reliable material humans have ever invented, and in one very specific way, it is. But there is a hidden weakness inside every single piece of plain concrete ever poured. A weakness so severe that without a fix discovered over a century and a half ago, almost none of the modern world you rely on would be physically possible. No skyscrapers, no highway bridges, no parking garages, no dams. By the end of this, you will understand exactly why concrete alone is not enough. What happens inside a concrete structure the moment it starts to fail, and why the solution is one of the most elegant engineering partnerships in history. This is not just about construction. This is about the hidden physics inside every structure you blindly trust every single day. Before we get to the weakness, let us understand what concrete actually is. Because most people think of it as one thing. It is not. Concrete is a mixture. Portland cement, water, sand, and crushed stone or gravel. When water meets cement, a chemical reaction begins. The mixture does not just dry out, it cures. The cement paste crystallizes around every grain of sand and every piece of aggregate, locking everything together into an artificial stone. That process takes about 28 days to reach full strength. And the result is remarkable. A cured concrete block can handle compressive loads of 3,000 to 5,000 pounds per square inch. That means you can stack an enormous amount of weight directly on top of it, and it will not move. Think of it like a hard biscuit. Press down on one with your thumb, and it barely budges. It resists. It holds. That is concrete under compression. It is doing exactly what it was designed to do. But now, try something different. Hold that same biscuit between both hands and bend it. It snaps almost instantly. Not because it is weak overall, but because the force you applied was not pushing down. It was pulling the two halves apart. That is concrete under tension. And that single distinction is where everything changes. Every structure in the world deals with two fundamental types of stress: compression and tension. Compression is a pushing force. It squeezes material together. Think of columns holding up a roof. The weight of the roof pushes straight down. The column is being compressed. Concrete handles this extraordinarily well. Tension is a pulling force. It stretches material apart. Think of a rubber band being pulled from both ends. The fibers inside are under tension. They are being asked to resist being torn. Concrete handles tension terribly. At the molecular level, concrete's crystalline structure is rigid and brittle. It has almost no ability to flex or stretch. When tension is applied, tiny internal cracks form almost immediately. Those cracks spread, and concrete fails suddenly, without warning, not gradually. Here is a simple way to see the difference. Imagine a sponge sitting on a table. Stand on it and it compresses under your weight. It holds. Now grab both ends and stretch it sideways. It deforms completely with almost no resistance. Compression and tension. Two completely different responses from the same object. Concrete is the opposite of a sponge in terms of strength. Enormously strong in compression. Dangerously weak in tension. And the problem is that almost every real structure in the world experiences both forces at the same time. Here's where common sense gets it completely wrong. Picture a concrete beam, a simple rectangular block, maybe 10 feet long, sitting horizontally, supported at both ends. Now place a heavy load in the middle. By common sense, a material that can handle thousands of pounds per square inch should hold that load without a problem. But here is what actually happens inside that beam. And this is the part that changes how you see every bridge you have ever driven across. When a load pushes down on the center of a horizontal beam, the beam bends. The top surface is being compressed. The material is being squeezed together. Concrete handles that just fine, but the bottom surface is being stretched. It is under tension. The two ends are fixed, the middle is being pushed down, and the underside of that beam is being pulled apart. And concrete cannot handle that, not even close. At roughly 1/10 the load that the compressed top surface could absorb, the bottom of that beam cracks. The crack does not stay at the bottom. It travels upward through the cross-section. Within seconds, the beam fails. A structure that looked completely solid, carrying far less weight than its compressive strength would suggest, collapses. It is like building a bridge out of dry pasta. Looked at from above, it seems solid. The pieces are tightly packed and rigid. But the moment the center deflects downward, the underside has nowhere to go, and it snaps. The failure is fast, total, and completely predictable once you understand the physics. This is not a hypothetical. This is what happened in the early history of concrete construction. Structures failed. Floors collapsed. Engineers could not figure out how to use a material that was abundant and cheap, but fundamentally unsuited to the real-world forces structures have to carry. Until one man started embedding iron bars inside it. In the 1860s, a French gardener and amateur inventor named Joseph Monnier began experimenting with ways to make stronger flower pots. He tried embedding iron mesh inside his concrete molds. The pots became dramatically harder to crack. He kept experimenting. Eventually, he patented reinforced concrete for use in pipes, tanks, and bridges. He did not fully understand the engineering behind why it worked, but the result was undeniable. Adding steel inside concrete transformed the material completely. Here is what is physically happening inside a reinforced concrete beam. The steel bars, what engineers call rebar, are placed specifically in the tension zones. In a horizontal beam, that means near the bottom. When the load is applied and the beam tries to bend, the concrete on top handles the compression. The steel bars on the bottom handle the tension. Each material is doing exactly the one job it is best suited for. Steel has a tensile strength of roughly 58,000 to 80,000 pounds per square inch. Concrete's tensile strength is somewhere between 300 and 700 pounds per square inch. Steel handles tension approximately 100 times better than concrete does. The two materials together create something neither one could achieve alone. Think of it this way. Concrete is the muscle that resists being crushed. Steel is the skeleton that resists being torn apart. Remove either one, and the structure fails at a fraction of the load it was designed to carry. Together, they become one of the strongest and most versatile building systems ever engineered. This is the moment where the "this should not work" logic finally resolves. That bridge you drive over every morning, that parking garage ceiling above your car, that 30-story concrete tower downtown. None of them are just concrete. They are a precisely calculated partnership between two completely different materials, carrying two completely different types of force. But here is the part of the story that most people never hear. And it is almost too convenient to believe. Steel and concrete should not get along. One is a rigid crystalline structure. The other is a dense metallic alloy. Mix them inside a structural element, and you would expect problems. Thermal expansion is the big one. When temperatures rise, materials expand. When temperatures drop, they contract. If steel and concrete expanded and contracted at different rates, the bond between them would crack apart within a few seasonal cycles. The structure would destroy itself from within. But steel and concrete expand and contract at almost exactly the same rate. Steel has a coefficient of thermal expansion of roughly 6.5 millionths of an inch per degree Fahrenheit. Concrete sits at roughly 5.5 to 7 millionths per degree Fahrenheit. The match is so close that over decades of temperature swings from -20 degrees Fahrenheit to over 100 degrees Fahrenheit, the two materials move together as one. That is not something engineers designed. That is physics hand in construction, one of the most useful coincidences in history. And there is another layer. Freshly poured concrete has a highly alkaline chemistry. That alkaline environment forms a passive oxide layer on the surface of the embedded steel. That layer protects the rebar from corrosion. Concrete is not just structural support for steel. It is chemical protection. The two materials actively preserve each other. But the system has a vulnerability. And when it fails in a way that is both predictable and devastating. Water is the enemy. If water penetrates concrete through cracks or through insufficient concrete cover over the rebar, it reaches the steel. Once oxygen and moisture contact the steel, corrosion begins. Rust forms. And here's the critical part. Rust occupies roughly 3 to 4 times the volume of the original steel it replaces. It expands inside the concrete like a slow-motion explosion. That expansion cracks the concrete from the inside out. The cracking allows more water in. More corrosion forms. More expansion happens. The concrete cover spalls off in chunks, exposing the rebar directly to the atmosphere. The cross-section of the steel bar reduces. The tensile capacity of the beam drops. And eventually, without visible warning from the outside, the structure loses the ability to carry its design load. This is not a rare scenario. This is the primary deterioration mechanism behind billions of dollars of infrastructure repair every single year across the United States. Bridges built in the 1960s and 70s are reaching the end of their design life right now. In large part, because of this exact failure sequence. The fix is not complicated. Adequate concrete cover over the rebar. Proper waterproofing. High-quality concrete with low permeability. Regular inspection. But when those steps are skipped or cut during original construction, the timeline toward failure is already running. Silently, inside the structure. Years before anyone sees a crack on the surface. Reinforced concrete changed the world. It made skyscrapers possible. It let engineers span rivers with bridges carrying millions of pounds of traffic. It gave architects the freedom to design shapes and spans that would have been completely impossible with stone or timber alone. But engineers did not stop there. Because even reinforced concrete has limits. The steel inside is passive. It waits for tension to arrive and then resists it. But what if you could put the steel under tension before any load ever arrived? What if you could preload the tension zone of a beam so that when the real forces hit, the concrete never reaches its cracking threshold at all? That idea is called Prestressed concrete, and it takes everything we just covered and pushes it an entire level further. If you think reinforced concrete changed what was possible, wait until you see what happens when engineers put steel under deliberate tension before a single pound of load ever touches the structure. That is where the real engineering gets strange.